Okay, today we are going to do trigonometry in 5 minutes. We're going to talk about the fundamental concepts that are involved in trigonometry. All right, here we go. To begin, we're going to start by looking at right triangles. We're going to take this perspective first. So here's a right triangle, and just in case you forgot, a right triangle does not mean it's correct all the time. It means there is a 90-degree angle. That means the other two angles, this guy and this guy, are called acute angles. And it's not because they're acute, it's because the measure of them is less than 90 degrees. And if you recall, the three angles of a triangle, they sum to 180. And that's true for any triangle, not just right triangles. So it's these two acute angles do add up to 90 because the whole thing has to add up to 180. Okay, now before we get into the trig, we have to talk about something called similarity. So we're going to make this triangle a similar one that is bigger. So the triangle on the right here, it's called a dilation. I made it grow larger, but I kept the proportions the same. So that means that the pink angles and the purple angles are the same. These two triangles have the same corresponding angles. They are equal. You can think of this as if you take a photograph of somebody, right? If you take a photograph, the picture is smaller, but the person maintains the proportions. It doesn't make their finger now is the same length as their leg, right? All the proportions are maintained. So every triangle that has, let's just assign angles here, that has a 90-degree triangle, that has a 40-degree and a 50-degree acute angles, they're all going to be similar. It doesn't matter if the triangle is huge, it's miles by miles, or if it's tiny, millimeters, or even smaller, it's going to be similar. That means the ratio of the corresponding sides is equal. It's like a photograph, right? These triangles are going to have the same proportions, so to speak. So without getting too much into the math of similarity, let's take a look at the trig. If you start talking to someone about trig, it won't be long before they start talking about sine and cosine. This is the abbreviations. This is how they look on the calculator. You also may hear them talk about tangent and cotangent and these other trig functions, but they're all based around these two guys, sine and cosine. So let's take a look at how they work. So for sine to work, when you're looking at a right triangle, you take the sine of one of the acute angles, so either the 40-degree or the 50-degree. So say you choose the 40-degree. So it's a function here, right? You're putting in the 40-degree into this sine function, and what pops out, and this is always the case with sine, it's the length of the opposite side. So that is the side over here divided by the hypotenuse. The hypotenuse is the long side across from the right angle. So it's this side and this side. So I labeled the triangle here. I gave the points here, ABC, big ABC, and then the side lengths, little ABC. So sine of 40 degrees is the length of side A there divided by the length of side C. And now because all right triangles that have a 40-degree angle are going to be similar, right? They're like photographs, right? They're bigger or smaller, but they're scale drawings, so to speak. This ratio is always the same. It doesn't matter if it's a big triangle or a small triangle. When you actually put that into a calculator, you get a number. And it's a number that is less than 1 and greater than 0, because there are no side lengths here, and that's because the hypotenuse, C here, is always the longest length of a right triangle. And that's the bottom number of your fraction. So the top number, the A here, is going to be smaller, so you know you're going to have a fraction. Or your calculator will give you a decimal. But your calculator's been programmed to know all these values. You could figure this out for yourself. If you have like you could make with a paper and a protractor, you can measure a right triangle as a 40-degree angle, and you cut it out really precisely, and then you measure this length here, right here, and then you measure this length here, and you divide them, you will get the same number that your calculator spits out. So that's how the calculator knows what sine 40 is. These can easily be figured out. Anybody can figure these out. Now let's look at cosine. Cosine is extremely similar. It's a ratio of the side lengths of this right triangle. If you take cosine of 40 degrees, instead of using the opposite side, use the side right next to it. You call it adjacent in math. So it's side B divided by the hypotenuse. And again, this is just a number, and it's always the same, regardless of how big or small this right triangle is. Now, first off, you might think, why is this even useful? Why is that ratio important? Well, let's just say you knew what the side length of A was. Let's just say A was 10. Okay, say you have a real life triangle here. It's 10 feet maybe. And you know you have a 40-degree angle there. You can find side length C by doing sine 40 degrees, and instead of A, you put 10 feet. And you can solve this for C. This is the basic algebra problem. Again, sine of 40 degrees is just a number, and then you solve for your variable C, and you can calculate that hypotenuse. So you use trig to find like missing side lengths of a right triangle. This is one use of it. Now, you may think that's kind of useful, but guess what? It's way more useful than that. So I wrote the sine of angle A, instead of putting that 40 degrees there. So this is any right triangle. And then I have cosine of angle A there, and I wrote the ratio. Now, using those definitions and a little bit of Pythagorean theorem and algebra, you can prove, you can derive the law of sines and cosines. So let me write those out for you real quick. So for sake of time, I just wrote law of sines. I can show law of cosines later. But this ratio here, sine of angle A divided by the side length A, is equal to the sine of angle B divided by the side length B, and then sine of angle C divided by the side length angle C. And it does not matter if we have a right triangle. Now, this works for any triangle, but it's derived purely on using the definition up here. You can derive this. So it is based on right triangles, but now it can be applied to any triangle. For example, say the triangle here, all you know is that angle B is 50 degrees, and you know these two side lengths. Well, you could use law of sines to find angle A, this pink angle, and once you find that, you could find the green angle by subtracting from 180, and you can use law of sines again and define this side length here. So you can find all the sides and angles by using the law of sines. And then if you combine that, the law of cosines, it's even more powerful, where if you don't know any angles, you can find the angles using law of cosines. You just know the sides. So triangles are everywhere, and being able to do this, finding missing sides and angles, is incredibly, incredibly useful. So I realized I've got over 5 minutes, and I've just looked at the right triangle, the triangle perspective of trigonometry. There's also the circular perspective. These are circular functions, and they can be graphed, and they have this periodic nature. It has a whole range of applications. So I'm going to make a secondary video, and I'm going to try to keep it brief, of showing that side of trig. If you understand both those perspectives and combine them together, that basically is the concepts, the big fundamental concepts of trigonometry.